In this section, we will talk about the effects of acceleratory forces on the body in aviation and space physiology. So, because of rapid changes in velocity and direction of motion in airplanes or spacecraft, several types of acceleratory forces affect the body during flight. At the beginning of flight, simple linear acceleration occurs. At the end of flight, deceleration occurs. And every time the vehicle turns, centrifugal acceleration occurs. Now, let's discuss the centrifugal acceleratory forces. When an airplane makes a turn, the force of centrifugal acceleration is determined by this relationship, in which F is centrifugal acceleratory force, m is the mass of the object, v is velocity of travel, and r is the radius of curvature of the turn. From this formula, it is obvious that as the velocity increases, the force of centrifugal acceleration increases in proportion to the square of the velocity. It is also obvious that the force of acceleration is directly proportional to the sharpness of the turn, or the less the radius. Moving towards measurement of acceleratory force. When an aviator is simply sitting in his seat, the force with which he or she is pressing against the seat results from the pull of gravity and is equal to the person's weight. The intensity of this force is said to be positive 1g because it is equal to the pull of gravity. If the force with which the person presses against the seat becomes 5 times the normal weight during pull-out from a dive, the force acting on the seat is positive 5g. If the airplane goes through an outside loop, so that the person is held down by the seat belt, negative g is applied to the body. If the force with which the person is held down by the seat belt is equal to the weight of the body, the negative force is negative 1g. Now, moving towards effects of centrifugal acceleratory force on the body in case of positive g. Firstly, let's discuss effects on the circulatory system. The most important effect of centrifugal acceleration is on the circulatory system, because blood is mobile and can be translocated by centrifugal forces. When an aviator is subjected to positive g, blood is centrifuged toward the lowermost part of the body. Thus, if the centrifugal acceleratory force is positive 5g, and the person is in an immobilized standing position, the pressure in the veins of the feet becomes greatly increased to approximately 450 millimeter of mercury. In the sitting position, the pressure becomes nearly 300 millimeter of mercury. In addition, as pressure in the vessels of the lower body increases, these vessels passively dilate, so that a major portion of the blood from the upper body is translocated into the lower vessels. Because the heart cannot pump unless blood returns to it, the greater the quantity of blood pooled in this way in the lower body, the less is available for the cardiac output. Note that both these pressures fall below 22 millimeter of mercury for the first few seconds after the acceleration begins, but then return to a systolic pressure of about 55 millimeter of mercury and a diastolic pressure of 20 millimeter of mercury within another 10 to 15 seconds. Acceleration greater than 4 to 6g causes blackout of vision within a few seconds and unconsciousness shortly thereafter. If this great degree of acceleration is continued, the person will die. Now, let's discuss effects on the vertebra. Extremely high acceleratory forces, for even a fraction of a second, can fracture the vertebra. The degree of positive acceleration that the average person can withstand in the sitting position before vertebral fracture occurs is about 20 G. Now, let's discuss the negative G. The effects of negative G on the body are less dramatic acutely, but possibly more damaging permanently than the effects of positive G. An aviator can usually go through outside loops up to negative acceleratory forces of -4 to -5 G without causing permanent harm, although causing intense momentary hyperemia of the head. Occasionally, psychotic disturbances, lasting for 15 to 20 minutes, occur as a result of brain edema. Occasionally, negative G forces can be so great, for example, -20 G, and centrifugation of the blood into the head is so great that the cerebral blood pressure reaches 300 to 400 mm of mercury, sometimes causing small vessels on the surface of the head and in the brain to rupture. However, the vessels inside the cranium show less tendency for rupture than would be expected. The reason is that the cerebrospinal fluid is centrifuged toward the head at the same time that blood is centrifuged toward the cranial vessels, and the greatly increased pressure of the cerebrospinal fluid acts as a cushioning buffer on the outside of the brain to prevent intracerebral vascular rupture. Because the eyes are not protected by the cranium, intense hyperemia occurs in them during strong negative G. As a result, the eyes often become temporarily blinded with what is called red out. Now, let's discuss the protection of the body against centrifugal acceleratory forces. Specific procedures and apparatus have been developed to protect aviators against the circulatory collapse that might occur during positive G. First, if the aviator tightens his or her abdominal muscles to an extreme degree and leans forward to compress the abdomen, some of the pooling of blood in the large vessels of the abdomen can be prevented, delaying the onset of blackout. Also, special anti-G suits have been developed to prevent pooling of blood in the lower abdomen and legs. The simplest of these applies positive pressure to the legs and abdomen by inflating compression bags as the G-force increases. Theoretically, a pilot submerged in a tank or suit of water might experience little effect of G-forces on the circulation, because the pressures developed in the water pressing on the outside of the body during centrifugal acceleration would almost exactly balance the forces acting in the body. However, the presence of air in the lungs still allows for displacement of the heart, lung tissues, and diaphragm into seriously abnormal positions, despite submersion in water. Therefore, even if this procedure were used, the limit of safety almost certainly would still be less than 10 G. This was all about today's video.
Explore our extensive library of over 1,800 video lectures to learn about a wide range of topics. Only on sqadia.com.